we talked about how current can generate a magnetic field, and that's the property behind what's called an electromagnet. Well, magnetic fields can also exert forces not just on other magnets, but on moving charges, on current. So an electric field, we learned earlier, exerts forces on all charges. So if you place a positive charge in an electric field, it will experience a force. If you place a negative charge in an electric field, it will experience a force on it. If you place an object that's neutral, that has zero charge or zero net charge on it, then it will not experience a force in an electric field, right? The force depends on the charge. You might remember the equation. The force for the electric field depends on the charge of the object times the magnitude of the electric field. If Q is zero, if there is no charge on the particle, the force has to be zero. Fairly straightforward. Magnetic fields, adds a layer of complexity. Magnetic fields exert forces on charges, but only if those charges are moving, right? If a charge isn't moving, there's no current. So there's no magnetic field generated by the moving charge. So magnetic fields exert forces on charges, but those charges have to be moving. If we want to know what the magnitude of that force is, like we have here, the force for the electric field was equal to the charge times the strength of the electric field. We want to come up with an equation that's similar for magnetic force. So the magnetic force and the magnetic field, and M is not used because M is already reserved for mass. So B is often used when talking about a magnetic field, often called the B field, which means magnetic field. The force, magnetic force on an object depends on the charge. Likewise with an electric field, magnetic fields can only affect charged objects. If the object is not charged, the magnetic field will do nothing to it. It has to be moving. It has to have some speed. If the speed is zero, the force is zero. It has to depend on the strength of the magnetic field. Just like the electric force depended on the strength of the electric field, the magnetic force depends on the strength of the magnetic field. And then finally, there's one additional term here, a sine function, theta, where theta is the angle between the particle's velocity and the direction of the field. So it's not enough that the object has to be charged. It's not enough that the object has to be in a magnetic field. It's not enough that the object has to be moving. It's how the object is moving with respect to the magnetic field. If the velocity and the magnetic field are in the same direction, so let's say the magnetic field is going to your right on the screen here, and the particle is going to the right, then the angle between the velocity and the magnetic field is zero. Sine of zero, plug it into your calculator, is zero. So there is no magnetic force. Likewise, if the magnetic field is going to your right, but a particle is going to your left, the angle is 180 degrees. Sine of 180 degrees is zero. So if the velocity of the particle is parallel to the magnetic field or anti-parallel to the magnetic field, there is no magnetic force. For the maximum magnetic force, we want this term to be 1. Sine goes between -1, 0 to 1, right? So sine, for the maximum force, we want this to be 90 degrees. So the magnetic field goes to your right, and the velocity goes to your right, and the particle is moving 90 degrees, either towards you or upwards. Then you get the maximum force on the particle. This equation just gives you the magnitude of the magnetic force. This equation gave you the magnitude of the electric force on a particle. The electric force for a positive charge was always in the direction of the electric field, if you remember. If the charge was negative, the force was always in the opposite direction of the electric field. So the force direction and the electric field direction were intimately related. Here, we'll learn in the next part of this video, the direction of the magnetic force depends on what's called the right-hand rule. And we'll talk about that in a little more detail in a bit. Now, the magnetic force is often called the Lorentz force. I rarely use that terminology. Your book does on occasion. So just note that if your book talks about the Lorentz force, they mean the magnetic force. Now, again, the particles here, the variables in this equation are listed to the right. If you rearrange this equation and solve for the magnetic field, you can learn the magnetic field depends on the force exerted on a particle, the charge of that particle, the speed of that particle, and the angle between the velocity and the magnetic field. So you can use this definition to basically calculate what the magnetic field must be given the behavior of a particle in that field. Magnetic field has SI units of what are called Tesla. Tesla is represented by a capital T. Magnetic field strengths of Teslas are usually incredibly powerful magnetic fields. A 1 Tesla magnetic field is a very powerful magnetic field. Prior to this, your book talks about an earlier unit for magnetic field called the Gauss, and that's still actually quite commonly used. How many Gauss is the magnetic field? Well, 1 Gauss, or I should say 1,000 Gauss, is equal to 1 Tesla. So the Gauss as a unit is 1,000 times smaller. You need 1,000 of them to equal 1 Tesla. To give you an idea, Earth's magnetic field strength is about half a Gauss. So it's a very weak field. Tesla is a much stronger, much more powerful unit, much bigger unit. It's like comparing inches to miles. I mean, that's the analogy there. So the SI unit, though, is Teslas. So if I tell you what the magnetic field is in Gauss, you should easily be able to calculate how many Teslas it is. Just basically divide the number by 1,000. So this is the units for magnetic field. Of course, the units for force is Newton. Unit for charge on a particle is Coulomb. Speed of a particle in SI units is meters per second. Magnetic field strength is Teslas. Angle, degrees or radians. Just make sure your calculator is in the right unit when you plug that in to solve these problems. Now, this will give us, once again, the magnitude of the force, but how do we figure out what the direction of the force is? For that, we have to introduce a concept called the right-hand rule. Now, the right-hand rule, you might have been taught this before in a math class or a previous physics class. So you do need to use your right hand. So for those lefties out there, I apologize. There is no left-hand rule. You must use your right hand. I have a drawing here showing an example to how to use the right-hand rule. So I have a magnetic field going to the right. Here I have a charged particle. Let's pretend it's positively charged, going into the board. Here I have a charged particle. Again, let's pretend it's positively charged, coming out of the board. So a little X in a circle usually represents that a vector or some object is pointing into the page. Think of it like an arrow. When an arrow is flying away from you, you can see the fletching, the feathers on the back of the arrow. When an arrow is flying towards you, you see the point of the arrow coming at you. So here a particle is going into the board, here a particle is coming out of the board. Let's pretend for the moment they're both positive. So for the right-hand rule, your book shows a couple of different examples. If you prefer to use the version in your book, you're welcome to do that. I prefer this version, so I'll teach it to you today. First thing we do is you place the fingers of your right hand in the direction of the velocity of the particle. So for example, for the particle going into the board, that means our fingers point into the board. For here, the particle coming out of the board, that means our fingers will point out of the board. Let's stick with this one first. Fingers going into the board. Push the velocity of the particle parallel to the magnetic field. So I'm going to use this as a little vector here. This little cap represents the forward direction of the particle. Back here is the tail end. So this is the particle is going into the board. My fingers are going into the board. I'm going to push this dry erase marker so now it points to curl my fingers around. So the particle going into the board, the vector points in the direction of the magnetic field. And the magnetic field is going to the right. So fingers in the direction of the first, curl, my fingers point towards this direction of the second, my thumb points in the direction of the force. So this particle will experience a force, let me draw it here in red. The magnetic force for this particle will be down. Okay, let's look at this particle. Figures in the direction of the particle. Push the particle onto the magnetic field. And again, if the object is coming out of the board, I'm curling my fingers, pushing the object towards the magnetic field. My thumb is pushing up. This particle will experience a force upward, the magnitude of which you calculate using the previous equation. This just gives you the direction. But you can see that the direction is always perpendicular to the plane formed by the velocity and the magnetic field. Right? Velocity is going into the board. Magnetic field is on the board going to the right. Force is either down or up. It's never in the direction of the velocity of the particle. It's never in the direction of the magnetic field. It's always perpendicular to those two vectors. What happens if we have a negative charge instead of a positive charge? You do the exact same thing with the right hand, except at the end you flip the force direction, like we do with the electric field. Right? The electric force is equal to the charge times the electric field strength. If the electric charge is negative, the force is in the opposite direction of the electric field. If the charge is negative here instead of positive, all you do is flip the force direction. So this is the force if the object is positive. The force will be in this direction if the object is negative. Here, this is the force direction if the object is positive. If the object is negative, we just change the direction. So here are the steps. Again, place the fingers in the direction of the velocity of the particle. Push that velocity parallel to the magnetic field. Your thumb will then point in the direction of the force. If it's positive, you're done. If it's a positive charge, you're done. You know what the direction of the force is. If it's a negative charge, flip that direction, 180 degrees. We'll do one more example here on the board to show this to you. But I just want to point out before we do that, magnetic forces, because they're always perpendicular to the velocity of the particle, they can never ever change the speed of the particle. They can only change its direction. So magnetic forces are basically a steering wheel. You can force a particle to turn one way or the other way. You cannot accelerate it, and by accelerating it, I mean changing its speed. Changing a direction is also an acceleration. So uniform circular motion, you might remember, you have an object in the center. There's a force inward on that object. Let's say this is the moon, and here's Earth. The moon goes around the Earth in a big circle. There is an inward force of gravity, right? That means that there's an inward acceleration, but the moon's velocity is always perpendicular to that motion. This is called uniform circular motion. You might want to go back to last semester's notes and get a refresher on that. But the acceleration, which is in the direction of the force, and the velocity are always perpendicular. So the speed of the moon never changes, its direction changes. Now, this is the simple example. In reality, the moon is not a perfect circle. But if it were, the speed wouldn't change, only the direction of motion changes. So when you're in your car and you have the cruise control set, you can accelerate your car when you go around a corner, you're accelerating. Acceleration doesn't necessarily mean changing the speed, reducing or accelerating or increasing your speed. It can also be a change in direction. Magnetic forces can only change direction. They cannot increase or decrease the speed of a particle. Unlike electric forces, which can both change direction and change speed, magnetic forces can only change direction. I'm stressing that because that's an important distinction between magnetic forces and electric forces. So let's do this right-hand rule one more time, but let's change the direction of the magnetic field. Let's have the magnetic field going into the board. So now I'm going to draw the magnetic field, a uniform magnetic field going into the board. And I'm going to have the velocity of the particle, well, choose to go in any direction. Let's look at a positive charge going to the right. That's its speed. What direction is the force going to be? Well, right-hand rule, right? Fingers in the direction of the velocity. push the velocity onto the magnetic field. In this case, I'm pushing the velocity into the board because the magnetic field is going into the board. My thumb is in the direction of the force. This positive charge will experience a force, magnetic force, upward at that instant. Let's look at a negative charge going down. What direction will the force be on this object? Okay, well, fingers in the direction of the velocity. Push the velocity out of the magnetic field. In this case, my fingers go down, pushing it this way. You can see my thumb is sticking up to the right. So the force for a positive charge would be to the right. This is a negative charge, so I flip it 180 degrees. So the magnetic force on this object will be to the left. So that's the right-hand rule. Be sure you are comfortable using the right-hand rule. We'll be using it a lot in this chapter. Again, your book gives a slightly different version of it. If you prefer to use the book's version, that's fine. Just be comfortable applying the right-hand rule to figure out the direction of the force of a particle moving in a magnetic field.